Hi, in this video we are going to be covering the Arduino's ADC module and have a better understanding on how we can actually program it in bare metal. Okay, so by the end of this lecture we will understand all the low-level registers that are involved in the ADC operations, and we'll also learn how to connect or interface an analog device to your microcontroller and perform the necessary ADC operations. Now, firstly, let's have a nice overview of the key features of the ADC module. Firstly, it's a 10-bit successive approximation ADC. So the result of this ADC is 10-bit. Okay, so there are a lot of ADCs in the market. Okay, so if you wish to integrate an ADC module into your project, okay, generally most microcontrollers already have a built-in ADC module like what we are having now for the Arduino. But at the same time, there are dedicated ADC modules out there, and if you think that you want something that is a bit better than what you already have in your controller, then you can think of getting an external controller. Okay, so an external ADC module, okay, and then interface that, okay, to your current microcontroller here. Okay, but in our case, since our microcontroller already has a ADC module, we will be using it. Okay, so since we have a 10-bit ADC, that is what we will deal with. Of course, if you are going with the option of interfacing an external one, then you can have a lot of options. Okay, so you have 8-bit, okay, 10-bit, 12-bit, 16-bit, and so on. Okay, so there are a lot of different types of ADCs that can be configured or connected separately to your controller. Okay, the conversion time is around 13 to 260 microseconds, and you have 8 channels. Okay, so for the 8 channels, you can select any one of them to do the A to D conversion. Okay, so of course, important thing to note is you have only a single A to D module. So if you look at the hardware inside the ADC module itself, it's just a single ADC module, but I have 8 channels, okay, that I can select from. So at any point of time, I can connect 8 analog devices to the controller, but I can only do one ADC operation at a time. It cannot be done concurrently. Yeah, so that is the important thing to note. You cannot do multiple ADC operations concurrently. You have to do them one at a time. Okay, now in terms of channels, we just said that it has 8 channels, but it is also important to note that only 6 are available. Okay, only 6 are available for the deep package that we currently have for the Arduino Uno board in our studios. Okay, so if you look down here, the analog to digital channels are all here, ADC 0 to ADC 5. Okay, so there are 6 channels. Okay, the additional channels, which are channel 6 and channel 7, are only available on the TQFP package. Okay, not on the other packages. Okay, so this is important thing to note, so that in general, most of us, when we get the Arduino board, it comes with the DIP package. Okay, so and the pinout that we get are also directly connected to ADC 0 to ADC 5, which is mapped to port C pin 0 to port C pin 6, pins 5, port C pin 0 to port C pin 5. So it is important to note that though the module itself has 8 channels, only 6 are available for us to use. Okay, so let's have an overview of ADC operation. So ADC, analog to digital conversion, basically means that we have an analog signal, okay, and we want to convert it to a digital. Okay, so analog to digital, and as we know, analog signals basically have an infinite range of values, in a sense that they keep on changing, correct? Whereas digital values are very finite. Okay, so if I say that the lowest value is 0, 0, 0, 0, 0, 0, 0, 0, the next higher value will be 0, 0, 0, 0, 0, 0, 0, 1, and so on, 0, 0, 0, 0, 0, 0, 1, 0, all the way to the topmost. Okay, so if I say I have an 8-bit ADC, then the highest value will be 1, 1, 1, 1, 1, 1, 1, 1. Okay, so what we need to do is we need to convert a continuously changing analog signal, okay, to a digital equivalent. Now when we do that, you can see that a few things has to be factored in. Firstly, it is the sample time. The sample time is how frequently am I going to take a snapshot of my analog signal, okay, and after I take that snapshot, which digital value do I map it to? Okay, which digital value do I map it to? Okay, so that is what we're going to be discussing now. So the first thing is sampling. Okay, sampling is basically taking a snapshot of the analog signal that is always changing. Okay, and we're taking a snapshot at it at periodic intervals. Okay, so that is what we call the sampling period. Okay, and of course, in terms of frequency, we call it a sampling rate. Okay, if you look at these three pictures here, you can see that if I take many samples, okay, I can reconstruct the, or if I try to connect back the dots, okay, I can sort of reconstruct the original signal or very close to the original signal. Okay, whereas if I take dots that are very far apart, okay, then I lose a lot of information in between and I may not be able to reconstruct it, okay, or as close as how it was originally. So the key thing is how fast should I sample it? How fast should I sample it? And that is already something that we know from EPP1, which is the Nyquist sampling rate. Okay, which basically says that now the Nyquist sampling rate says that the sampling rate must be at least greater than or equal to 2 of Fmax, where Fmax is the highest frequency component in your analog signal. Okay, so if I have a signal, for example, our human voice, that is having a range of 20 Hz to 4 kHz. The highest frequency component is 4 kHz, so I should sample at least 8 kHz. You can sample higher than 8 kHz, okay? That is not an issue, but sampling lower is an issue, okay? So we'll not go into the details of that, okay? But for now, we just take it that sampling rate must be greater than or equals to 2 times Fmax, okay? Now, the second thing that we said is once we sample, okay, I need to assign it to a digital equivalent value. Okay, so these are what we call the quantization levels. Okay, and the number of quantization levels I have depends on the number of bits that I have to represent these levels. Okay, so if I have a 8-bit ADC, okay, that means my values are ranging from 0000 0000 all the way to 1111 1111. So total of 256 quantization levels. Okay, 0 to 255. Now if I have more bits, that means I have more levels. And what does that mean? Okay, basically what we are saying is that this range of digital values will be mapped to the range of analog values that your converter is going to handle. So in this case, if I say I have an 8-bit A to D, all zeros, which is the smallest value, will map to 0 volts, and all ones will map to 5 volts. Okay, so that brings us to the next thing, which is the resolution. Okay, so the resolution is basically the voltage distance between two adjacent levels. Okay, so what does that mean? Okay, so if I go back to the earlier example, if I have a signal that is changing and the one signal has a value of 0000 0001 and the next signal 0000 0010, I mean I'm talking about two consecutive samples. So in terms of digital representation, we say that they both differ by 1. Okay, but when they both differ by 1, what is the equivalent voltage difference? Okay, so that voltage difference, okay, is what we call the resolution, the voltage distance between two adjacent quantization levels. Okay, and to calculate that, we take the high minus low divided by 2b. Okay, in general, okay, in our case, we say we're operating at 5 volts for the Arduino, so we say 5 minus 0 divided by 2 to the power of 10, okay, because it is a 10-bit ADC. Okay, so that is how you calculate the quantization, the number of quantization levels as well as the resolution. Now, let's now go into the programming procedure for the ADC module. To program the ADC, okay, so there are a few steps involved. First step is to activate the power to the ADC module. Okay, so there are a few peripheral devices within the Arduino that are not powered up by default, so you need to make sure that if you want to use it, you need to make sure they are powered up. Okay, so in order to activate power to the ADC, you need to write a 0 to the ADC bit of the power reduction register. Okay, so we have seen this register before, and we will see it again in the future. And this register, if you look at it, it basically contains the bits to decide which of the peripheral subsystems will be powered. Okay, and this is also important because, as you know, for our mini project, okay, power consumption is also one of the factors. So we want to reduce power if we are not using the modules in our system. Correct. So once you activate power to the ADC module, we want to switch on the ADC explicitly. Okay, so to switch on the ADC, you need to do write a 1 to bit 7 of the ADC SRA. Okay, so this is the status register. Okay, ADC control and status register, and bit 7 is basically to enable the ADC. Once you enable the ADC, what you want to do is to select two things. One is the channel, and the other one is the reference voltage. Okay, the channel basically, as we said, for the Uno the controller on the Uno board, we have 6 channels. So we want to select which channel we are going to read the analog signal from, and the reference voltage. Okay, so that is inside the AD mux register. And once all of those are configured, we will be able to start the conversion. So to start the conversion, we write a 1 to bit 6, which is the AD analog to digital start conversion bit of the register. And I then need to wait. Okay, as we saw just now in the earlier slides, I need to wait for a few microseconds for the conversion to be complete. Okay, and once how do I know it's complete? I have to poll bit 6 again. Okay, because once I write a 1 to bit 6, okay, which is the ADSC bit, it will remain 1. Okay, and when the conversion is complete, it will become 0. Okay, so I keep on pulling the bit, and once it is done, I can now read in the converted value. Okay, and to read in the converted value, you have to remember it is a 10-bit result. Okay, so the 10-bit result is stored into 2 registers, ADCL and ADCH. So I need to read from both the registers and combine them to get a full 10-bit result. Okay, and basically that is about it. And if I want to keep on repeating it, then I go back to start step 4 and keep on repeating the whole process depending on the number of samples I want. Okay, so let's have a look back at the registers. Okay, so the power reduction register, as we said just now, is to switch on or to turn on power or turn on or off power to different peripheral blocks. So for the ADC, which is over here, I need to write a bit 0. Okay, then it actually is turned on. Okay, so that is the first step. Okay, write a 0 to bit 0 of this register to turn on power to the ADC module. Okay, and the code is shown below. Subsequently, we need to enable the ADC again. That is to basically write a bit 1 over here. Okay, and by writing a bit 1, you are able to enable the ADC or switching it on. Okay, now the next thing is the prescaler value over here. So the prescaler value is basically determining the sampling frequency. Okay, and sampling frequency is given by f clock divided by ps. Okay, so our f clock, as you know, our board is 16 megahertz, and divide by whatever prescale value you get, that is the sampling frequency that you will be using for the program. Okay, so these are the prescaler values, okay, that you can use. And basically by setting the appropriate prescaler value, you are going to take 16 megahertz divided by the prescale value to give you the sampling rate that you want. Okay, and basically that code is given over here. Okay, so this ADC SCRA, if you come back here, okay, so basically what you're doing is only here and here. Okay, we are going to ignore the other bits for now. Okay, so this is the statement to set up the ADSCRA register. Next is the mux register. The mux register basically is doing two things. Okay, firstly is the reference, and then the mux. Okay, so for the mux, okay, so for the reference, we are going to be using 01, which is the AVCC with external capacitor. Okay, and why we are going to do this is because the Uno board already has the hardware configured as such, so it's easier to use this option as the reference voltage for the A to D conversion. Okay, so that is what we're going to do over here. For the conversion channel, that means your multiplexer selector, we are able to configure the bits depending on which channel we want to use. Okay, mux 0, 1, 2. So as you can see, there's another mux tree here, but we are not going to be worried about mux tree. We're just going to be focusing only on mux 2, 1, and 0. Okay, and depending on which channel we want, so if I want channel 2, then I just set this to 2. Okay, and this is the channel 2, and this is the reference voltage, ADC reference. Okay, so that's about it for the AD mux register. Okay, so the next step is to read the result. Okay, so once the conversion is complete, the result will be stored in two separate registers. Okay, ADC-L and ADC-H, because it is a 10-bit result and all our registers are 8 bits, so we have two registers. So what we need to do is, very importantly, we always need to make sure that we read from ADC-L first. Okay, because if we read, once we read from ADC-H, it causes ADC to override. Okay, both ADC-L and ADC-H with new values. So because the hardware is configured as such, it is important we follow the sequence that we read from ADC-L first, okay, followed by ADC-H. Okay, and since our result is actually 10 bits, what we need to do is the ADC-H, the value ADC-H, we need to shift left by 8. Okay, so this is actually what we are doing here, shifting left by 8, and then we are adding with ADC-L. So this whole thing will give us a 10-bit result. Okay, now once we get this, then basically we are done. Okay, the ADC is complete. So the last part is to understand the mapping. Okay, so the mapping, as I said in the beginning, we have a 6-channel ADC for our Arduino Uno board, a microcontroller, and ADC 0 basically maps to port C pin 0, ADC 1 to port C pin 1, and so on. Okay, so this is a mapping, and it's also mapped to our header pins, okay, directly over here. So it's easy for us to access them for our studio as well as our project. Now let's see it in action. Okay, basically what you will be doing for our studios, first activity is to connect up the circuit where we have a flex sensor connected to A0, okay, which is input 0, a channel 0 of the ADC module. And basically by flexing the sensor, we will be able to measure different voltages at the A0 pin, and eventually we will be using that to control the LED. Okay, so let's see the code for this. Okay, so the first thing is, we went through, we need to power on the ADC module that is in the PRR register. Okay, and once we power on, we can enable the ADC, okay, followed by setting the appropriate p-scalar values. Okay, and then we set the reference voltage that we want, which is 0, 1, okay, which is the AVCC reference, followed by selecting the channel. So in this studio activity 1, we're going to be using channel 0. Okay, so the last 3 bits will be 0. And then finally I set the port B pin 5 as output. This is for the LED, okay, to be blinking. And once the setup is done, okay, all I need to do is to now start the conversion. Okay, so if you remember, to start the conversion, I write a 1 to the ADSC bit. Okay, and once a 1 is written to the bit, the ADC conversion will start, and that bit will remain 1 while the ADC conversion is going on. And once the ADC conversion is complete, it will become 0. Okay, so it will change to 0 once the ADC conversion is complete. So I will be stuck in this loop while I'm waiting, okay, for the ADC to be complete. Once it is complete, I read the register, the results from the two registers, ADC-L, ADC-H, and pack them together into a single variable ADC value. And after that, here I'm just toggling the LED and calling a delay routine here to loop, okay, or to delay this loop based on the actual ADC value that I get. Okay, and basically once I'm done, so this is considered I've completed one sample, and if I want, and since this is a loop, I'll continuously go back and keep on sampling the data again and again. Okay, so that is basically what you're going to be doing for the first part of the studio, which is the polling approach. and later on we'll be switching over to the interrupts, okay, for the next part of the ADC studio. And finally we'll also be integrating the PWM element from our earlier studio into this studio. Okay, so we'll have both ADC and PWM running concurrently. Okay, so that's about it. Okay, and we will see you in the studio. Thank you.